Thanks for the organizer to give me the opportunity to talk about one of our newest results. So the title of my talk, Formation of Rocky Planets and Super Earth in Systems with Migrating Giant Planet. I put this system up because this is the system that started the whole business. The first extrasolar planet was discovered in 1995. If we consider extrasolar planets around the main sequence of stars. So in 1995, for a high school graduate, 18-year-old getting into college, that may be the first time that person heard of extrasolar planets, right? So if you are 43 years or younger, you may not know the whole story. So let me tell you that. If you are in your 20s or 30s, you grew up with it. Most likely you don't know the story. So I'm going to tell you the story behind this whole thing. Why this is important, where it came from, and how it resulted into a bunch of questions and what the work that we have been doing. We heard this morning that one of the biggest things that extrasolar planets gave us was planet migration. Planet migration had actually been worked out from fundamental physics in 1988, 1986, by Doug Lin and John Papaloizzo. This is the paper. If you are interested, get on it. This is planet migration they're talking about, that because of the tidal interaction between protoplanets and disk, protoplanets migrate and they can go inward or outward. So one of the best things that we learned from extrasolar planet is that theorists are not always wrong. You know, once in a while we say things that make sense, you know. So here comes the first extrasolar planet is discovered, is on 4-day orbit, so it has migrated. So Doug Lin goes back with Shigeru Ida. They put a paper out and they say that, with Peter Bodenheimer and Derek Richardson. They put a paper out. They said that there must have been planet migration. This you all should have seen. If not, please go ahead and read it. And then planets come in. Radial velocity starts finding planets, and there are many Jupiter-sized planets enclosed in orbit. This is Upsilon Andromeda, the first multiple planet system discovered. And then the story starts from here. When Jeff Marcy et al. and Fossa in 1998, they discovered this planet. They discover around Gliese 876 is an M star, and they discover a planet on 60-day orbit, a 2 Jupiter mass planet on 60-day orbit. So this was all good, and you know, nothing unusual. In the meantime, there was this guy who suggested that planets can migrate in and out, and put the formalism for it out there. And then a year after that, that group, the John Papaloizzo group, formulate all that into hydrodynamic and develop the code Fargo and everything. And so then came the what is it called? Type 1 migration, where the planet migrates and doesn't open a gap. Type 2 migration, planet opens the gap and everything. So all that was going on. And again, back to this one. In 2001, another planet was discovered around this star. And now you have 2 planets, one in 30-day orbit, one in 60-day orbit. One is 2 Jupiter mass, and the other one is half of Jupiter mass. So this immediately raised question that can planets migrate and get captured into resonance? I just showed you that a few years prior to that, things had been worked out. So people go back into, oh, that's my phone. Thank you. When you live in Hawaii, you have to tell 2 people where you are. Let me tell you. I'm terribly sorry.
Might be important.
Whoever that is. Just put it on mute. Yeah. You have to tell 2 people you are 4 hours, 10 hours ahead. So anyhow, so planet migration, people go back and study planet migration and how they capture into resonance. They work that out and everything. And in the meantime, another planet is discovered around this system. And that's where questions come in. So a planet discovered, a super Earth planet discovered at a 2-day orbit, and people started asking questions that how can planets of a small mass in a super Earth or a smaller regime form close to the star with migrating giant planets? So that was the question that was put forward. Let me explain this a little bit more. We later on discovered that this has a 4th planet sitting farther out. So Now the system has 3 planets. The 3 planets are in a Laplace resonance. It has a super Earth, and because of the perturbation of these 3 planets, this region cannot maintain any object in there. In other words, the system is dynamically full. So this was all good, and everything worked out. It was not, it turned out that it was not the only system with this type of properties. 55 Cancri is another one, and Gliese 581G is another one. Regardless of whether you believe on planet G or not, there is a giant planet with super Earth sitting interior and exterior. So that brought up all these questions. And the rest of my talk is to show you how we address these questions, and I'm going to finish by answering them. System with migrating giant planets form terrestrial planets, and can these planets be habitable? What would be the frequency of these planets? Are giant planets necessary for delivery of water and volatiles? Do systems with giant planets have asteroid belts? Can closing giant terrestrial planets form in situ? And can giant planets form interior to terrestrial planets? All these questions came from what I just explained to you. And then people started working on it. This morning, Stephen Kane gave a fantastic talk, and the punchline was that if you want to understand extrasolar planet, you've got to understand the planet you are standing on. This is the best. Solar system is the best system that we know. And models that we develop for the formation is based on the knowledge that we have from this. And the only thing that we can do with extrasolar planet at the moment is to find a way to extend those models to extrasolar planets. So I'm going to, briefly, for about 60 seconds, I'm going to explain what this is. And this is the model of formation of terrestrial planets. And I'm going to address some of the properties of that. And then I get you into how this addresses some of the questions that I just explained. So when we want to form terrestrial planets, the customary and traditional model is to take a bunch of planetary embryos, submerge them in a bunch of small kilometer-sized bodies, put your giant planets anywhere that you want. That's freedom that you have. And then let everything interact with each other through gravity. And let's run them. And then see what happens. Here, I deliberately put Jupiter and Saturn on the current orbit. And I'm going to let this run, and then I'm going to stop it. Oh, shoot. Everything is going wrong. Could you stop it at a certain point? Just to stop the simulation. Yeah. Oh, okay. So I need you to, okay, hold them like that. Okay. Hold on. Okay. Go ahead. You do it.
You want me to pause it?
Yes, pause it now. Thank you. Good. So these lines that you see, these are caked with gaps. Now. So those lines are caked with Okay, perfect. Just hold it like that. So these lines are caked with gaps. You get all this area cleared up because of the perturbation of Jupiter. That little thing that you see up here, by the way, this is eccentricity. That little thing that you see up here is the eccentricity of the embryos and planetesimals are excited because of the effect of Saturn, because this is the secular effect of Saturn. Now, this acts as a barrier. Anything in front of that is immune from giant planets, it forms planets. Anything above, beyond that is not immune, it doesn't form planets. That is why we have asteroid belts. That is why terrestrial planets form here. Okay, so that answers a few of the questions that we had before. We can continue now. I'm running out of breath. Okay, so let us run, and then and I give it a sip of water. Thank you. So it keeps going. It gives you terrestrial planet. It gives you, we can stop it. Yeah, it gives you a big object in the asteroid belt and everything. I chose that, like I said, on purpose to say a few things. These type of simulations are extremely stochastic, and they suffer from several fundamental issues. One of the issues they suffer from is because they're stochastic. The other one is that when we treat collision between them, they're perfect merging. I'm going to get that in a few minutes. But this was the state of the art at that time, and people applied that to migrating planet. They took giant planets, they let it migrate into the same field that I just explained, and then studied what comes out of it. So this addressed some of the questions there that you may get a variety of different systems if you let giant planets migrate. And then subsequent to that, it was the work by Sean Raymond and Avi Mandel who showed that if you have a very heavy disk with a lot of material in behind the giant planet as well, you may actually form planets beyond the giant planets. So as giant planet migrates, you may actually form planets here as well. This was all good and everything, but like I said, the issue with these systems is that that collisions is perfect merging, and that is one big problem. I wrote an article about all this in the annual review, and I put these two slides up to show that you can have migrating giant planet, and then you will get variety of different systems depending on how rapidly object moves. The rate of migration is you can also produce system of double giant planets and super Earth similar to GJ876. So this all has been done, except that this is one of the problems. The two objects, they don't physically hit each other. When they come close to each other, the code considers them merge. You can imagine that cannot be realistic and introduces a lot of approximation and assumption into the simulations. In reality, however, this is what happens. Objects hit each other and break each other into pieces. This is the current state of where terrestrial planet formation is going. If you're interested, I'll be happy to talk to you about that. But 2 years ago when I was here, I gave a detailed talk about this type of simulations. This is what we are doing now. However, I'm not going to talk about that here. I'm going to talk about the old style, the traditional style. The traditional style, the good thing about it is that it's fast. The bad thing about it is all these things that I said, but the good thing about it is fast. And more importantly, if you do several hundred of them, you can use the result and study things and statistically, which gives you a feeling of the proof of concept. You may not be able to produce a model that is quantitative or make predictions, but you will be able to handle the physics, be able to understand those questions from the physics point of view. So that's what I'm going to do. That's what we did. This is the current, I'm going to get to results. That's what we did during the past 2 years. We ran the old style of doing planet formation. We ran several hundred of them for a variety of rate of migration and different numbers of planets. And I'm going to walk you through this. These are my last 3 slides. I'm going to walk you through this and I'm going to finish my talk. It may sound like previous ones, but there is a lot of physics here. For instance, look at these. Depending on rate of the migration, depending on where the planet stops, you may get closing giant planets with multiple terrestrial planets. If what causes the planet to stop, oh, I missed one. Yeah, if what causes the planet to stop is weak and the planets keep going, you can get very closing planets with terrestrial planets, or you can actually get hot Jupiters, or your planet crashes into the star, right? So this all tells you what you see, this diversity that I just showed you from Kepler, it all depends on the planet-disk interaction, how strong the gas in the disk is to hold the planet or to let it go. And so I'm going to show you the same thing with 2 planets. Here, the second planet is outside the range that I have plotted, but it actually comes in and it eventually appears, and the same for this one. You see the similar properties here. You see the similar properties for next one. Oh yeah, this is the next one. For 3 planets. So the bottom line is that what you see happening from the observation, what you get, point to one very important point, and that very important point is that what dictates what happens at the end is the planet-disk interaction, is giant planet-disk interaction. And the amount of gas that existed. If you see that the planet stops there, and there is a lot of stuff in front of it, those peas and nuts in front of it, that is because that system got rid of its gas at that time. And if you see that giant planets are rare, because giant planets, those systems that don't have giant planets, have so much gas that let the giant planets crash into the central star. So I'm going to finish my talk by going through, next slide, please. Next slide. Next one. And next one. There you go. Can systems with, can I have my water? Thank you. Can systems with migrating giant planet form terrestrial planet? Yes, if the disk of embryos does not have, oh, there is a word have missed here, does not have too much mass to cause the giant planets to migrate too fast. The planet-disk interaction is what dictates where the giant planet stops and whether it crashes into the star. Can such terrestrial planets be habitable? If the condition above is satisfied and the disk carries enough water, the formed planet may contain necessary water. I'm not talking about whether it can originate life or not, but as far as water, it is possible. What would be the frequency of terrestrial planets is unknown. The reason for it is that these type of simulations are stochastic. More importantly, much more importantly, what we see is the final product. We don't know the initial condition. We don't know the dynamical evolution. What we see is after all that has been done. Are giant planets necessary for daily water? No. Water and volatiles are transferred from one object to the other through the interaction of embryos and their successive collision. Remember those hydrodynamic simulations, SPA simulations showed you? That is how it goes. Giant planets only speed up the process, but the process has nothing to do with giant planets. You can remove giant planets and same simulations will form terrestrial planet for you. It takes maybe 150 million years. Next slide. Do systems with giant planets have asteroid belts? Yes and no. It all depends where the giant planet stops. In our solar system, giant planets stop wherever they are now, and it left enough room for the disk in front of it to develop asteroid belts. But if they move, then like GJ876, and create a full, dynamically full system, no. Can closing giant planets form in situ? Giant planets cannot form in situ. This is a talk by itself. And the reason that, 10 seconds reason for it, you need slow collisions, you need efficient collisions, and you need gas. And this all can be accommodated in certain part of the disk and not at the places where terrestrial planets form. Can giant planets form interior to terrestrial planets? No, they cannot. You have seen all these models come out and they say, well, they form hot Jupiters in situ and everything. But what happens then is that they can migrate, and as they migrate, like I showed you, they may hinder the formation of other planets and planets to larger sizes and keep them small. Thanks so much.